Hello, and welcome to Unit 4. Back in the house, but you can't see my dog because she's under the covers, because that's how she sleeps. So, we are jumping into thermodynamics. Thermodynamics is a huge part of the test, the AP exam, and it's not that difficult. It's a couple equations, which are on your reference table, and a couple things that you have to think about, but overall it's not too bad. It's very applicable to any chemistry courses you would take in college. A lot of this stuff I talked about pretty frequently when I was in college. So, potential energy diagrams. We're going to be looking mostly at this equation between hydrogen and oxygen to get water. Alright, so this is what our potential energy diagram is going to look like. Our y-axis will be energy, and the x-axis will always be time. Your reactants will always start on the left, and you'll always have products on the end or the right-hand side. And you'll always have this bump here, and that has to do with the amount of energy it takes for that reaction to occur. At this bump, an unstable arrangement of atoms forms momentarily. So here we have just our oxygen and our hydrogens. When we get to here, we have this weird blob of reaction, and then when we're down here at the products, we have water. This number right here is called the activation energy, how much energy it takes to get over that hump. And then up here, this is called the transition state. That's what that is called. That is like the top point. Okay, sorry. My dad keeps texting me, so I keep pausing. Okay. Yeah, don't remember what I was saying, but we'll move on. Alright, so we can have either an endothermic or an exothermic reaction. We have talked about those two words. Endothermic is when the surroundings become hotter, and so your system feels colder, so the heat travels from the system to the surroundings. Exothermic is when the heat comes into your system from your surroundings, and it feels like your system is hot. So I think of it like a cup. If I'm holding a cup, it's exothermic. The heat came to the cup, and I feel warm holding it. So here we can see a couple things. So we have our reactants still right here. We still have our products down here. Depending on what this jump looks like, will determine if it's endothermic or exothermic, or technically the endothermic or exothermic determines what the jump looks like, but either way. So the heat of our reaction, delta H, which is a very important term, is going to be the difference between your reactants and your products. The difference in energy between those two things. And you'll actually see the equation later. The activation energy, we talked about that, is the distance between the reactants and the energy it takes to make that reaction happen. So this was an exothermic reaction where the reactant's energy is going to be higher than the product's energy. An endothermic reaction is going to look like this. In an endothermic reaction, our reactants are going to actually be lower than our products. So our reactants start down here, products are going to be much more, and that activation energy is a lot more. And this is going to be our endothermic reaction, meaning the heat goes from the system to the surroundings. So the delta H of reaction, delta H is actually the heat of the products minus the heat of the reactants, or the energy, same difference. The products is actually more here than the reactants, so our delta H is actually going to be a positive number, whereas with our exothermic reaction, delta H was a negative number because the products are less. a catalyst is going to increase the rate of the reaction by lowering that activation energy barrier. This is what a catalyst does. Our reactants and our products will have the same energy as they did before. There is no change to the energy of the start and the end. However, there is a change in how much energy it takes to get to the product. So the activation energy with the catalyst is lowered compared to just the normal without the catalyst. The heat of reaction is still the same though, because our reactants and our products don't change in energy-wise. And that's just random questions to go along with the lecture. So the enthalpy of reaction is going to be your delta H. Delta H is the heat that is released or absorbed in a chemical reaction. We're going to be looking at the heat contained within the products and the heat contained within the reactants to figure out that delta H number. And that delta H number is pretty important in thermodynamics. We can do a lot of equations with that number. So looking at a thermochemical equation, CH4 gas plus O2 gas yields CO2 gas plus H2O gas, a lot of gas. Delta H of the reaction, and we'll talk about what that little symbol means, the little circle, in a little bit. Don't worry about it right now. But that delta H of the reaction is going to be equal to negative 890 kilojoules per mole. That negative number tells me that it's an exothermic reaction. So this delta H refers to the reaction exactly as it's written. So with these amount of moles, so there's 1 mole of CH4, 1 mole of O2, 1 mole of CO2, and 1 mole of H2O. That is the delta H for that certain number of reactants and products. So exact same thing that we were looking at. So we start off with a CH4 molecule and 2 O2 molecules, and we will yield 2 CO2 molecules and a CO2 molecule and 2 H2O molecules, and that takes 890 kilojoules to go from this side to this side. And that 890 is true when there is 1 mole of CH4, when there's 2 moles of O2, 1 mole of CO2, and 2 moles of H2O. Now, what would happen if we took that same reaction, which is this one, but we doubled the amount of reactants? Well, we doubled the amount of CH4. We have now 2 moles of CH4, methane, and excess of the O2. So if we had 890 kilojoules for 1 mole of CH4, how many kilojoules will we have for 2 moles of CH4? All we do is we double that number, and it would, we get 1780 kilojoules for those 2 moles. So it would be per mole. So we can now do some calculations. It says calculate the enthalpy change associated with the formation of 3.8 moles of H2O. Here's my delta H of the reaction, negative 890 kilojoules per mole. For H2O is what we're looking at. I have 1 mole right here, so 890 negative kilojoules per 1 mole. And it's just to simple find the x over 3.80 moles. And I get x to equal 3,382. Oops. And that's going to be a negative number. Kilojoules per mole. Simple, just multiply by 380 moles to get that x. Example number 2, it says calculate the enthalpy change when 5.45 grams of NH3 reacts with excess oxygen. So we don't even worry about the oxygen, there's excess of that, but we see 5.45 grams of NH3. Right here I have 4 moles, and my delta H of the reaction is negative 902 kilojoules per mole. So the first thing I'm going to do is convert that 5.45 grams of NH3 to moles. 5 grams of NH3. Simple stoichiometry here. I put my molar mass on the bottom. My molar mass is 17.034. I get 0.3199 moles of NH3. If I have negative 902 kilojoules per 4 moles of NH3, I'm trying to figure out what is my delta H per 0.3199 moles of NH3. My delta H, after I calculate that out, I just multiply both sides by this number, and I get negative 72 kilojoules per mole. Example number 3. It says determine delta H of the reaction if 15 liters of nitrogen monoxide forms at STP. I see the words STP, or the symbol STP. I see a volume of a certain compound, and I need to determine the delta H of the reaction for that. I have the delta H of the reaction, but I'm going to guess that the moles is not the same as the moles right here, which is 4. So if I have 15 liters at STP, I can do PV equals nRT. PV equals nRT. Pressure at STP is 1 atm. The volume here is 15 liters. Moles is what I'm looking for. R, we're going to use 0.08206 because that is in liters atmospheres per mole Kelvin. And then I will use my Kelvin at STP is 273. I get N is equal to 0.6696 moles. I do my simple find the X equation. If I've got negative 902 kilojoules per 4 moles of NO, how many kilojoules do I have per 0.6696 moles of NO? And you have to use the same compound on both sides. And I get my delta H of the reaction to be 150.99 kilojoules per mole. I'll rewrite that because I just deleted it super fast. 150.99 kilojoules per mole. And you can calculate that yourself. Super easy equations to do right there. So moving on, what would be the delta H reaction of the bottom reaction? So if we're starting with a CH4 and two O2s and we get to the two H2Os in the CO2, well, what if we start with the back half? Well, it's just going to be the opposite delta H reaction-wise. So if you have a positive going one way, it's negative going the other way. Simple as that. So what does that little circle mean? In our delta H, we call that delta H naught of our reaction. The delta H naught and other thermochemical values with that naught sign, it just means the standard thermochemical conditions, which are 25 degrees Celsius, 1 atm. If it's solid or liquid, it's pure, and for solutions, it's one molar. If you see that little circle, it just means those conditions. So next we're going to figure out delta H using bond enthalpies. Bond energy is the potential energy of valence electrons. They're going to decrease as they approach the nucleus of another atom. So potential energy, not kinetic energy. So the potential energy of the electrons decreases as they approach the nucleus. So their kinetic energy increases as their potential energy decreases. So as they get closer to other nuclei, they feel the attraction, basically, for lack of better terms. Energy is always released during the formation of a bond. Potential energy decreases as the atoms move closer together. So there's always going to be energy released during formation of a bond, as there's also, because there's energy released as it's breaking, and then energy released as the formation of the bond is happening. The same amount of energy must be added in order to break that specific bond. So if the bond's going to break, then the same amount of energy needs to happen. Potential energy increases as the atoms move away from each other. So your potential energy gets bigger as the less attractions there are. So delta H is going to, this is like a crazy slide, delta H is going to equal the sum of the bonds broken minus the sum of the bonds formed. And they will tell you what the bond enthalpy is for each bond. The bond enthalpy is the amount of energy required to break a bond, which is equal to the amount of energy released when that same bond is formed. So when we are right here, and we're going up to 2, in order to break this bond, a certain amount of energy must be absorbed. If we're going from here down to here, the same amount of energy is released. And if we're going from 2 to 3, the AB bond is formed and a different amount of energy is released. So there are different kinds of energies for those things, but if we're going just from 1 to 2 or 2 to 1, it's the same amount of energy. So in an exothermic process, more energy is released during the formation of the bonds in the products than is required to break the bonds. So when we're forming the bonds, so the product side, there is more energy happening than when we are breaking apart the bonds. The products are lower in potential energy than the reactants, which gives us that curve that we saw earlier where it looks like this. Our products are lower in the energy, because this is energy on this axis, than the reactants. Products down here, reactants up here. So up here, there is less energy to get up that hump than there is in forming that bond down here. For an endothermic reaction, that's when we see a graph like this. Our products have a higher potential energy. Products have a higher potential energy than the reactants do. The reactants are down here. There's less energy in the formation, so this amount of energy is less than when we have to break the bonds. Breaking the bonds is a lot harder in the endothermic reactions. So let's look at an example. Calculate the enthalpy change for the following reaction using the table of values. So they're telling us if there's a CH bond, this is the bond enthalpy. If there's an OO bond, there's 495 kilojoules per mole. We also have single and double bonds, and then an OH bond. So if I look at my equation, I have 4 CH bonds, so I'm going to have 4 of these, 4 of those. I have 2 O2 bonds, so I have an OO, I have 2 of those, and these are my reactants. I have 2 CO bonds, because CO2 is going to look like this. So I have 2 CO double bonds, so I have 2 of these. And then I have 2 HO bonds, because my O is in the center here, and I have 2 HO bonds. So if I'm going to do my delta H is going to be the bonds broken minus the bonds formed. So the bonds broken are these, and the bonds formed are these. So bonds broken is my reactants, bonds formed is my products. So I just fill in the numbers. 4 times my CH bond enthalpy, which is 413, plus 2 times my O2 enthalpy, 495, all subtracted from 2 times my CO double bond enthalpy, 799, plus 2 times my OH enthalpy, which was 467. And I do all that, and I get a delta H of 110 kilojoules per mole. And this is an endothermic reaction because the energy, there's less energy during the formation. making my delta H positive. Moving on, I have another equation. I have H2 plus O2 yields 2H2O with a delta H of negative 572 kilojoules. And it says, calculate the average bond energy in an HH bond. So it doesn't give us the HH bond, but we have one right here, and we need to calculate that bond enthalpy. So what I'm going to do on a fresh slide, I have negative 572 equals, I'm going to do the bonds broken minus the bonds formed. So, hold on here. So, yeah, sorry. Thought I did this wrong. Okay, so I have two H2s, 2 times my X, which is what I'm looking for. I don't know the H2 bond enthalpy, plus my O2 bond enthalpy, which is 495. And it's just one of those because it's just that. All subtracted from 4 HO bonds. Sorry, HO bond enthalpy, which is 467. And I have 4 of those. Oh, that's ugly. Because I have this thing going on right here. This is already 2, but I have 2 of those H2Os. So multiply the whole thing by 2 to get 4. And I get negative 572 equals 2x minus 1373 plus 1373 to both sides. And I get 801 equals 2x. Divide both sides by 2. And my x is equal to 400.5. And that's kilojoules per mole. And that's my HH bond enthalpy. All right, and that is all for this. Next time you're going to talk about calorimetry, which is our next way to figure out delta H. And we'll move on from there.